Okay, so we continue where we had left in the last class. We had found the reaction forces at A and B, and we were supposed to find the shear forces and the bending moments at this point C over here. Okay, so the way to proceed is this: make a hypothetical cut at X from A as long as the cut is left of W. Okay, so you want to make a cut anywhere you want from here until this point. Okay, the whole idea is that this W should not be on your left side. I mean, it can be, but we are just taking this approach right now so that this becomes more clear. So once you make this hypothetical cut, you get this section X and the other right section is L minus X. You get these two sections, and after this you have to make these internal forces which were actually internal at this point, any point over here. Now they will become external over here. So these now become external with this hypothetical cut. So that's how you have made that cut. Now, two things about this. The directions of V and MB are taken in accordance to this positive sign which we have seen before. They are oppositely directed in the two free body diagrams according with the Newton's law, but they bear the same labels. Since the left hand free body, the face of the cut has an outward normal directed in the positive x direction, while in the right hand free body, this one, the face of the cut has an outward normal directed in the negative x direction. So that's why you have this V in this direction. Okay, so that you can use the same symbol. Now the part after this is quite simple. For this part you have to balance the forces in the x direction. That would make it V plus Ra is equal to 0, and then you would also have the moment balance. That would be Mb is equal to Rax. So all these are scalar quantities because their directions are well evident in the diagram. Okay, so this implies that V is equal to minus Ra, and then you plug in Ra from over here. That would make it as minus Wb by L. Similarly, Mb is equal to Wb by L into x. So at any point x from A, the shear force is equal to this, the bending moment is equal to this. Okay, and if you want to find at C, x becomes equal to whatever value is there at C. So in this case we have taken it as x. So that's how you find this, and we'll now be seeing a way to draw the variation, because as a designer you may not actually be interested on how the shear force is, what shear force is at this point, this point, this point, this point, and so on. Maybe you just want to know the overall behavior of how the shear force will be on this entire beam, and same for bending moment, so that if you are interested say in the maximum value, you want to choose a material which can sustain that maximum possible load. Okay, so that's, so you are more interested in the distribution, and if you see that there is one part of it which is experiencing a lot of say shear force or bending moment, you can use some sort of a reinforcement in that point so that they are able to sustain that amount of forces or moments. Okay, so for this, I mean, the whole point is that you want to find the maximum force and moments, because from the designer, I mean, this beam will fail only when it reaches the maximum value is beyond what the beam can take in. So that's where you want to get into this. Okay, and this will be playing a big role in chapter 6 and 8 when we see it later on. So the graph which shows the shear force plotted against distance, that's called a shear force diagram. And then there is also a bending moment diagram. So V of X or MB of X. And in the next section, right now, we'll see how this happens. So let's look at this again to this diagram, where now we have shown the same problem. We have now shown RA and RB with the values which we calculated. Okay, so I'm sorry, this is actually WA and WB. It's not in the subscript as is shown in your figure. Okay, so you can make that correction in your book. Okay, so once this is done, you want to now draw the shear force diagram. So look at V. That value is equal to minus WB by L, and if you take it as a function of X, well, it seems it's a constant value as long as you don't reach this weight W. Okay, you have basically considered only the left part of it, so that part is clear. Okay, so you have a minus W by L. Now look at the bending moment for this part, that is WB by LX. This is clearly a linear straight line. Okay, and it goes to this place all the way until W acts. Okay, now this is how you have drawn this, and it seems you have achieved what you wanted. But hold on, I mean, the beam doesn't actually end over here. Okay, the beam doesn't end at X equal to A. This is the point X equal to A. Okay, where this W is acting. What about the part between this weight and the end to the end B? So for that you have to just so this is actually true when X is between A and uh, X is between 0 to A. Okay, you want to find it for between A X equal to A to X equal to L. Okay, so for that what you do is you just do this force and moment balance for this left hand side, and that would happen by writing V is equal to RB, and this RB you can take in from, where did it go, here, this feeds in, that makes it equal to WA by L, and similarly MB will become equal to just the moment balance you want to take from this point. That would make it an RB of L minus RB of L minus X. Okay, and this is where, so this is at sort of the cut now is made at X equal to A, which is where W, so that's why W is not appearing in this one. Okay, so once you have this, you will be able to plot the shear force as WA by L for the part which is between here and here, and MB will now have a negative slope, and it will be this particular part. Okay, so that's how you draw a shear force diagram and a bending moment diagram. So what does all this tell us? It tells us a few things. The most important thing is that this beam experiences the maximum bending moment at this point where this weight W hangs. Okay, and hence the beam must be, so all these, I think you should make all these corrections. Okay, some of these values, there's no subscript anywhere. Okay, so that's how you have to use it as a designer, and this is something you have to really get comfortable in to be able to draw the shear force diagram and the bending moment diagram, and we'll keep on seeing this in the further cases which we deal with. Okay, now let's learn about distributed loads. So in the previous section, you had assumed that the load acting on the slender member and the forces, support forces, were concentrated, or they were point forces. I mean, look at this. All this was a point force. It was acting at one specific point. So in many a times, you may not have these point forces, but instead have a continuously distributed loading. So look at figure 3.7 over there. Okay, so there's a beam which is subjected to a distributed loading of parallel forces. So the direction of the forces is shown to you, and they may be either, say, a fluid or a gas pressure, or from a magnetic or gravitational attractions. The origins of the force are irrelevant, and the point is that the beam experiences this sort of a distributed loading. So let me just sort of try to motivate why can such a thing happen. So look at this container, and you fill it with fluid. Okay, now as the pressure, if the pressure over here is P atmosphere, which is exposed to the atmosphere, and the height of the container is h, for example, the pressure will vary from P atmosphere to this maximum value, and this pressure over here will be P atmosphere plus rho g h. So here this value is P atmosphere, but it keeps on, I'm sorry, let me just remove this. Okay, so the value increases to P atmosphere plus rho gh, where rho is the density, and it will keep on varying like this as you go down into the container. So this is clearly a distributed loading. I mean, this face of the tank is experiencing a continuously distributed loading. Of course, it's much nicer than it looks over here in the sense it's linear, but the idea is the same. It's not a point force anywhere. Anyways, so when you come back, so let the total force on a length delta x, okay, this is the length delta x, and let the total force be denoted by this delta f symbol. Okay, the direction is shown. The intensity of the loading is given by q is equal to limit delta x tending to 0 delta f by delta x. This is what is called the intensity of loading. and it has the dimensions which you can easily find out. Okay, force per unit length. So in engineering work, the most common distributions are the uniform distribution, where Qx is constant and linearly varying. Okay, so Qx can have a form like Ax plus B. This is a linear variation of intensity, and we have just seen a example of how a fluid in a container, or I mean, even lithostatic pressure is of a similar. I mean, if you want to say bury something deep into the ground, you want to build a tunnel, or just for any mining purposes, etc., you have to go down, and then the pressure there will be much higher, but the overall behavior will be a linear pressure behavior. Okay, now this is how in most of the applications are. However, they won't be limited to this, but this is how it can be taken for simplicity. And you know that it can be as complicated as it. I mean, mathematically, you have the tools to solve it. Okay, now to avoid error in dealing with the distributed loading, it is convenient to adopt a sign convention for loading. We shall consider the loading to be positive when it acts in the direction of a positive coordinate axis. Okay, just like previous case. And in this case, the positive forces are Fy and Fz. Okay. So this is the convention for loading, in which case the loading is distributed. Okay, so let's consider this example in front of us. Okay, this one. Okay, there you go. So it's a cantilever beam. So any beam is called a cantilever beam if it is fixed in the wall like this. Okay, this is fixed, and I mean, as you see, it is deeply buried into the wall, so there's no motion, no displacement, no rotation at this end, and this is something which is called a cantilever beam. Okay, so the beam is AB and it is built in at the right end, which is shown in the figure. So now you have bricks which have a total weight W have been piled up in the triangular fashion. So the total weight is given as W, and they have been piled up in a triangular fashion. It is desired to obtain shear force and bending moment diagram. Just like in the previous case, we are supposed to find the shear force and bending moment diagram, meaning you have to consider this for this entire length. Okay, so let's see how you would proceed to draw the shear force and bending moment diagram. And this is sort of a revision of what we have just done, so if you have missed out the method, here is another chance. Okay, so the loading has been idealized, so this is the actual, again this is the model. So you have a linear varying distribution which is shown as Q is equal to minus W. Q is the intensity, remember, and then it is W naught by L into X. Okay, so W naught is this pressure, and this is very much like the hydrostatic pressure in the example which I had given. Okay, so this is your W naught, and it starts from 0 and reaches up to this value W naught. So when X becomes equal to capital L, it becomes equal to W naught. Okay, so that's the first part of it. Now the maximum intensity, as you know, is present. So the W naught is unknown for now, and we'll somehow be able to relate it to the total weight. I mean, you know, you can integrate it over the area and somehow you'll be able to find it. What happens at the wall is more interesting. So cantilever beam is fixed, so there's a clearly a reaction force, okay, and this force actually prevents any movement in the vertical direction of this end B, and then you also have a bending moment so that there is no rotation, so that constrains the rotation of this point B. Okay, so this is called the clamping moment MB by the authors of your textbook. So this is a free body diagram of the entire system which you have. So let me just remove this so that, okay. Now you want to find first the support reactions. Remember the previous question? You first find the support reactions, which was RA and RB. Okay. You want to do the same over here. Good part about life is, at least as you do this question, is that there's only one support to take care of. Okay, so the reaction at RB can be obtained from the requirement of vertical force balance. So you would do is this, you would write that the summation of forces in the y direction is 0. Okay, so what are the forces? RB minus integration of 0 to L W dx equal to 0. Okay, so that would give you RB is equal to W naught L by 2. This is what you have to assume. Okay, so this is how you have taken, I mean you have taken it in the very same area that for a small delta x the total weight acting will be W delta x, and the moment you take the limit as delta x tending to 0 you are able to write this term and you can get the value of RB. Okay, so RB is W naught by L, and that you will do by substituting W, and you have to integrate it over from 0 to L to the entire length. So that solves your sort of reaction force at B. So this is A, this is B. Okay. One of the good things is that you have actually also found the relationship between W naught and capital W. Okay, so if you look at this term, it is RB which is taking care of the entire weight W. Okay, so if you want to write this as equal to W, and this implies that W naught by L by 2 is equal to W from here. Okay, so you get this relationship. So W naught is equal to 2W by L. So that way you can find out. Okay, so this is essentially this figure which we have written over here. Okay, so the total weight balance is what we have done. Okay, so once this is done, you want to find the bending moment at the edge B. Now you want, again, I mean straightforward as it can be, you have to make a hypothetical cut. Okay, and you can make that cut over here. So from 0 to a value x, okay, 0 to this value x, you hypothetically cut it. Now the shear force and the bending moment over there is what you want to find. So you would now apply to obtain MB, we use the requirement of moment equilibrium about the point B. Since RB passes through B, it does not contribute to the moment around B. To obtain the moment of the distributed, we again use integration. the small element in figure 3.9c. So let's first come to this part itself. I mean, let's not worry about the hypothetical cut now. Let's find the bending moment, because right now we are only trying to find the MB at B, okay, not in the beam itself. So we don't have to worry about hypothetical cutting right now. Okay, so this should be easy. What you do is you RB, if you want to balance the moment about this point B, there's only practically one thing to take care of. One is the MB itself, okay, which acts like this, and then there is the weight, which you have weight of the bricks. So they will apply this force. Okay, so the lever arm, if you come out like this, the lever arm would be L minus X, this particular distance from B, and you write 0 to L. So once we do this, we'll have to write it as 0 to L W L minus X dx plus MB. Okay, so this must vanish for the equilibrium, and that's how we essentially write this term. Okay, so okay, so essentially this entire weight, this force, and R cross F, R is this L minus X, F is this W delta X. So for a delta X tending to 0, you can integrate it over the entire length and find this. So that's how you write the bending moment, and this MB will come out to be at X equal to L, which is at B, will come out to be as WL by 3. Okay. Okay. So you are sort of done with finding the reaction forces and moments at the supports, which is B. There was only one support in this. Now is the next part, which is to be able to find the shear force and the bending moment in the interior of the beam. At any interior point, if you want to find the shear force and bending moment, what would that be for this loading? So to do this, you have to take an arbitrary section of length x, okay, and can be anywhere from 0 to the final L. This time, because there is no concentrated load hanging there trying to distort what we were doing. So any part, I mean, if you take this, and the bigger triangle will be something like this. So they will all be similar triangles. So you don't have to worry about it. This x can be anywhere from 0 to L. So take a arbitrary section of this length x, and you consider its free body in this diagram. Again, just like the previous case, you take this small symbol delta E, let me call it E over here, and we are not using the symbol x because x is taken already now. Okay, so we are using this delta E, and the weight acting on this small part will be W into delta E. Okay, so W is the intensity which we have over here. Now E starts from here and goes until the middle, and hence this part is called delta E, and the remainder part would be x minus E. So you want to now do this force balance for this. That would be V minus 0 to x W into dE, that would be equal to 0, and So this is just the forces in the y direction. So V is already there, and then the only other force is this weight, but that has to be integrated over this entire length. Don't take the length as 0 to L because you are only dealing a certain section. That's why it's going only the until X. So this should give you V as W naught X square by 2L, and then you balance the moments. That would be MB. This is the internal. So the moment you make a cut, just like the previous case, this V and MB, which were actually internal, become external. Okay, that's what happens with a hypothetical cut. Okay, so MB plus 0 to X would be W into X minus E dE equal to 0. Okay, so you are calculating it from over here. W acts like this force will be W into dE, and then it will act over the lever arm X minus E, and that's how you have this term. So this should give you an MB is equal to minus W naught X cube by 6L. So you want to now draw a shear force diagram. It's easy. You already have a V versus X. You have to just draw it. So at X equal to 0, it will be this, and it will vary in a quadratic fashion. MB is equal to minus W naught X cube, okay, by 6L, and that's you plot over here, and it's easy. Okay, and as expected, and as you know from your experience also, in case this cantilever beam ever has to break, I mean, look at this from your own intuition, from your own experience. If this beam ever has to break, it is most likely to break at this edge. The reason for that is obvious. Both the shear force and the bending moment are at its maximum value. So somehow if your material cannot take this maximum value, it will break, and it will break from over here. So that's the advantage in trying to do this. And you try to break anything, say a piece of biscuit or a matchstick or anything else which you try breaking around, most likely the point from which it breaks is where it experiences its maximum bending moment. So that's where that is what is of help to a designer. Okay, fine. Okay, so the next section, which is section 3.4, is about the resultants of distributed load. So you have already, perhaps in your first year, studied what is the equivalent system. Okay, you had this complicated arrangement of forces and moments, and you would simplify it to find an equivalent force or moment system. Similarly, this resultant of distributed loads is just trying to simplify a complicated a distributed loading into a simpler arrangement of forces and moments. So two systems of forces are said to be statically equivalent. Okay. Statically equivalent if it takes the same set of additional forces to reduce each system to equilibrium, and we'll see what it means. A single force which is statically equivalent to a distribution of forces is called a resultant of that distribution force. So I mean, the idea is that if you have a distribution of forces like this, can you just replace by a single force? And you have done this in your mechanics. I mean, if you remember, you have this sort of a triangular distribution. What you would do is you would find the area of this, and then let it pass through the centroid of this triangle, which is 1/3 from the base, So that is the equivalent system which you have for this distributed loading. So let's see it in the light of the slender members. Okay. Okay, so one of the restrictions which you have is that you have distributed loading, and it is convenient to work with resultant of the distributed load rather than work with the actual distribution. I mean, there's a lot of integration involved and so on, and so the only thing is that this works only when you are evaluating the external reactions on the member. Okay, it is not allowed when internal forces and moments are calculated. So in trying to find this Ra and Rb, it's okay, but the moment you cannot do it for the internal bending moment or the shear forces. So we will illustrate that using an example like this. So consider two similar beams which is shown in this figure. Okay, and it is clear that the loading on beam B is the resultant of the loading on beam A. Okay, so on beam A you have these two P's acting. All you have done is replace these two with this 2P acting in the center of these two forces, which is the centroid of this. Okay, and the external support forces are the same. So Ra and Rb is exactly what applies to this case. The internal forces and moments and the deformation of the beams are very different. Okay, so you have seen that even though they are statically sort of equivalent and external force systems are same, but internal distributions are quite different. If you want, you can do this calculation and see for yourself what would be the V and MB of X in each case. Okay, so you consider now one dimensional loading, parallel forces, intensity Q of X. We have already seen that. Okay, and to determine the magnitude of its resultant, you want to find the resultant of this. Okay, and its location. You write the actual equations of equilibrium twice, once using the actual load and once using the resultant R at X. The two sets of equations must give identical reaction forces if R is to be resultant. So take a sigma Fy, and then you take it from 0 to L Q dx. That would give you this the entire force, the area under this curve. Okay, now what are the other forces? Ra and Rb, that's 0. For the equivalent, I mean this R is this equivalent force over here, and if you, that means you can replace this entire distributed geometry by this one force R, and it acts at this distance x bar from the origin. So if it is indeed the resultant R, then they must give identical reaction forces. Okay, this is what we have just learned. I mean, the internal ones don't matter, but the reaction and the external forces must be the same. So in this particular case, for the actual, this is the case. For the resultant, you want to do the same, and then you would find R minus Ra minus Rb equal to 0. Okay, and similarly for the actual, again you will have Ma is equal to 0 to L. Okay, and then you have X as your lever arm, and the force will be Q dx. So delta X, I mean when X tends to 0, you are just writing it as Q dx minus RB into L equal to 0. Okay, so RA will not appear because you are taking the moment about this point, and RB will have a lever arm of L. Resultant will not have Q clearly, so it will have MA is equal to Rx bar minus RB of L equal to 0. Okay, now the conditions on R and X bar are such that R is equal to 0 to L Q dx, and how have we found it? We have found it using this and this, these two equations. Okay, they must, R is giving out the same value. Similarly, you can write X bar is equal to 0 to L X Q dx by R. Okay, that is by this and this. This you can find out using these two equations. So if they are resultant, both of them should be the same, and it should give the identical reaction forces, and hence you have it. So that is the sort of derivation for the resultant forces and where it should act. So please read the textbook very patiently for this once you are done with this lecture, and you may have to read it several times and see the videos on and off just to be comfortable with this idea. It does take time, and the language has to be quite clear to all of us. Okay. So this is, as you know, is sort of the centroid of a loading diagram. Okay, and this is the total area of loading diagram. I mean, you knew this already, but so I mean, the very first things which you learn in mechanics is to find the centroid of any two-dimensional or three-dimensional surface or three-dimensional volume. So you would know that X bar, for a two-dimensional case, this is how you would find the area. So this was just for a one-dimensional case, okay? So we didn't have to do all that. But for a two-dimensional case, I mean, you can do it. Okay, and similarly for a three-dimensional case, you would have X bar is equal to X dV by integral dV, and similarly Y bar and Z bar can be found out. Okay, so the integrals in all cases will extend either over the length in a one-dimensional case, or the area in a two-dimensional case, or the volume in a three-dimensional case. So I don't think it should be a problem at all. And similarly, you can find the same method you can be using to find the parallel force system. So that all is given in your textbook. You can just see this later on. It's just that you will have some sort of a multiplying factor. Okay, so those things will be dealt much in a better way in examples rather than theory. Okay, so that's where we are right now. So let's take one small example, and again, I mean, it's simple enough for all of us. Let's take this figure 3.12. Okay, and this is the example which we have just dealt about the brick, which is the collection of bricks and a cantilever beam and so on. Okay, you want to now solve this using the resultant force. Okay, so now if you look at the B figure in this, you have replaced this distributed loading by a resultant force which acts at a distance of x bar from this. Okay, and RB and MB are as it was in the original problem. So you already know what R is. It is the area of this loading diagram, and that's half into base into height, so that would make it half into W naught into L. Similarly, x bar is the centroid of this triangle, which is 1/3 from the base and hence 2/3 from this end. Okay, so this is 1/3, so the centroid of this is 1/3 from the base and hence 2/3 from this part. So that is what we have written over there. And the external supports RB and MB now can be, now using this, it's very easy to find the external supports RB and MB. So you want to find RB and MB, sigma Fy will be equal to RB minus R is equal to 0. This would imply RB is equal to R, and that is W naught L by 2. Similarly, the moments also, so sigma MB can be found out by R into L minus X bar, okay, plus MB equal to 0. Yes, about this point you have taken the moment, so RB will not appear, and that should give you MB is equal to minus W naught L square by 2. So if you look back, it seems it's the exact same answer which you had earlier, is it? Yeah, okay. So it gives you the same answer which you had before. Okay. Okay, so these values are identical with those obtained in the example 3.3, and there's no problem with that. Again, I'll repeat, this method does not allow to find internal V and MB. Only external is okay. I mean, this RBMB is fine, and we have made that claim before, and we are making that claim again. So within the beam, you cannot do this for the result using the resultant of the distributed loading. But just like the last time, you always have a way around it. You can't do it for the internal forces and moments, but you can do it for the external ones. Trick around is quite simple. Make a cut section such that this internal force and moment actually becomes external. So this V and MB now becomes external, and now you can use this resultant force of a distributed loading to solve your problem. Okay, so now what will happen, you take a cut of X, okay, and then for this particular one, R would be what, the area under the curve, which would be half into base, which is X, into height. Okay, so that's what you would be finding out, and that would be W naught X. I'm sorry, I should not use this. Into base into height, okay, and that also there will be an L, so that becomes your R, which is the area, this total area, and you want to find this value, that is equal to W naught X by L. Okay, this value is W naught X, it's a linearly increasing, so it has to be W naught X by L. Okay, and the next is clearly you would want to find where does it act. Well, it again acts 1/3 from the base and hence 2/3 from this, so this is where this R dash acts. So let me call this R dash. Okay, So x dash is again x dash bar is 2x by 3. Okay, and once you have this, you can, just like in the previous case, find the Vx and MVx. So even though this wouldn't work for the external internal, by this hypothetical cut which you are making, you can make these forces as external to it, and you can solve this. Okay, so it seems a good progress until today. Please do not ignore any part, especially with drawing the shear force and the bending moment diagram. First of all, they are extremely important for an engineer, as you have seen. They are the most primal things which you learn about in this course, in courses which are like machine design, material selection. So this is like the bedrock of whatever you would want to do with anything related to solid mechanics in your future. Okay, and this is one of those important interview questions as well. If you ever sit for this any company which is slightly technical, at least slightly technical, they'll, this is the first thing which they ask about. At least they used to. I mean, at least a couple of years ago, things may have changed. Okay, so we end our class today now, and we'll be beginning with the differential equilibrium relations in our next class. So thank you.